In last lecture, we are discussing about what is the difference between microcontroller and microprocessor and introduction of microcontroller. Now, next topic is block diagram of 8051. In this block diagram, this is the block diagram of 8051, which contains CPU, 4 kilobytes ROM, 128 bytes RAM, timers, serial ports, input output ports, bus control, interrupt control, and oscillator. This is the block diagram or architecture of 8051. First, oscillator. It is an on-chip oscillator unit whose output produces clock pulse to synchronize the internal operations of 8051. One has to connect a crystal externally to control the frequency of the clock pulse. For operating the microcontroller at 12 megahertz or less, a quarter crystal of 12 megahertz is used. That means the crystal frequency of this crystal is 12 megahertz. One can also connect an external clock pulse. We can connect external clock pulse. Second is bus control. This unit is used to control the activities occurring on the bus like flow of data, address or control signals. That means data bus, address bus or control bus. This unit helps in transferring control of bus to various units of 8051 for transferring information or addresses. Third one is program memory, that is ROM memory, whose size is 4 kilobytes. This capacity of this ROM is 4 kilobyte. Any application's code is stored in the program ROM. The program counter is used to access information from the program ROM. It points to the addresses of the instruction which is to be executed next. There is a provision for memory expansion in 8051 and an external ROM can be interfaced if more program space is required. Means as per our requirement we can extend our memory of 8051s. Next is a RAM whose size is 128 bytes. This RAM is used to hold the operands or results of an operation. Means this RAM is save the data. Next is a input output ports. There are 4 parallel input output ports capable of handling 8-bit data each. Hence 32 pins of 8051 are devoted to transfer data parallelly. These ports are referred to as P0, P1, P2, P3. These ports are bidirectional. Port 0 to port P0, P2, P3 can be used as input output ports, but they also exhibit specific functions related to 8051. Hence these ports exhibit dual function. Exceptional case in these ports, only P1 does not exhibit dual function and is used only as a input output port. Next is serial ports, which is used for serial communication for sending or accepting the information. The RxD means received line on this port is used for receiving serial data from outside, and TXD means transmitter line is used for transmitting out serial data. The hardware inside these ports converts parallel data from the CPU to serial data for serial communication, serial transmission to outside, and also the incoming serial data to parallel from before sending it to the CPU. Timer 2 can be programmed to decide the baud rate for serial data transfer. The SCON means SCON, SBUF, SBUF, and PCON registers along with TMOD register, TMOD register are the special function register used for establishing serial data communication between the microcontroller and the outside world. Outside the world. Next is timer unit. The on-chip timer unit of 8051 helps to provide accurate timing for various control applications. The timer unit can also be used as a counter for counting purposes, and it can also be used for to decide the baud rate for the serial data transfer. There are two 16-bit timers in 8051 called timer 1 and timer 0. These timers can be configured to work in different modes like 13-bit timer, 16-bit timer, 8-bit auto, reload timer, or split timer. The timers can be activated through hardware signals as well as through the software instruction. The special function register associated with the timer units are TMOD and TCON, TH1, TL1, TH0, TL0. These are the timers. And next is interrupt control. This unit is responsible for processing external interrupts. It allows external devices to interrupt the microcontroller for variety of reasons and also serves the interrupt request. Interrupt means disturbance. Disturbance in programming or working of 8051. There are two types of interrupts, external and internal. It allows external devices to interrupt microcontroller that will be generated by various blocks like timer block and serial communication block of the microcontroller. It is also responsible for servicing multiple interrupt requests by checking for their priorities. These are two There are two interrupts which can be generated externally. These are INT0 and INT1. Out of this INT0 and INT1, INT0 has a higher priority than INT1. This is the one line answer, short answer. The special function register in the interrupt units are IE and IP. IE means interrupt enable and IP means interrupt priority. IE and IP. This is the two registers. And last is CPU. It is the heart of microcontroller. It is responsible for executing the instruction, performing calculations, and taking decision by checking required condition. Next is architectures. There are two types of architectures. First is von Neumann and second is Harvard. Von Neumann architecture and Harvard architecture. The von Neumann architecture was first proposed by computer scientist John von Neumann. In this architecture, one data path or bus exists for both instruction and data. As a result, the CPU does one operation at a time. It either fetches an instruction from memory or performs a read-write operation on data. So an instruction fetch and a data operation cannot occur simultaneously, sharing the common bus. This is the block diagram of von Neumann architecture. In this block diagram, there is program ROM, variable RAM, and stack RAM. There is three buses: data bus, address bus, and control bus. In between processor and registers, there is memory interface unit and instruction decode unit. Second one is Harvard architecture. The Harvard architecture offers separate storage and signal buses for instruction and data. This architecture has data storage entirely contained within the CPU, and there is no access to the instruction storage as a data. Computers have separate memory areas for program instruction and data using internal data buses, allowing simultaneous access to both instruction and data. This is the block diagram of Harvard architecture. There is program ROM, register, processor and register interface, PC stack, and instruction decode. This is the difference table of von Neumann and Harvard architecture. This will be asked in exam for differentiate between von Neumann and Harvard architecture. First difference is single memory to be shared by both code and data. In Harvard architecture, separate memories for code and data. Second difference is in von Neumann architecture, processor needs to fetch code in a separate clock cycle and data in another clock cycle. So it requires two clock pulses. In Harvard architecture, there is only one single clock pulse. In von Neumann architecture, third difference is higher speed, thus less time consuming. Speed is high, then time consume less time consuming process. In Harvard architecture, slower in speed, thus more time consuming. Last, von Neumann architecture, simple in design, and in Harvard architecture, complex in design. You can add one more point about cost. Last difference of von Neumann architecture, simple in design in this table. So we can make also one difference. Cost of von Neumann architecture is low or cheaper than Harvard architecture. The complex designing of Harvard architecture, so that's why its cost is high. Next is CISC architecture and RISC architecture. CISC and RISC architecture. Full form of CISC is complex instruction set computing is the full form of CISC, and reduced instruction set computing is the full form of RISC. Second difference is larger set of instruction. Full form of CISC is complex instruction set, so that's why larger the size of instruction. And in RISC, reduced instruction set, so that's why smaller set of instruction. Third is easy to program, and RISC difficult to program. Next is simpler design of compiler considering larger set of instruction, and in RISC complex design of compiler. Next is many addressing modes causing complex instruction formats. In RISC, few addressing modes, fixed instruction format. Next of CISC. In CISC, instruction length is variable, and in RISC, instruction length is varied. This is the common difference. In CISC, higher clock cycles per second means frequency of clock pulse is high, and in RISC, low clock cycles per second means frequency is low. Next is emphasis is on hardware. In a RISC, emphasis is on software. In a CISC, control unit implements large instructions set using microprogram unit. In a RISC, each instruction is to be executed by hardware. Next is for CISC, slower execution. In a RISC, faster execution. Last of CISC, pipelining is not possible. In a RISC, pipelining of instruction is possible considering a single clock pulse. This is the most important difference table.